During the last segment, we discussed the various parts of a turbine and how they work together to produce power. We didn't cover how the points where the turbine shaft passes through the casing are sealed. The gland seal and the gland exhaust systems do this job. Now, to see how these two systems work, we must understand the effects of pressure in a turbine. In simple terms, we can say that pressure produces a pushing force and vacuum a pulling force or suction. The creation of a vacuum in the last stages of a turbine helps the turbine operate more efficiently. Pressure varies inside a turbine depending on load. At low loads, many of the later stages in a turbine may be under a vacuum. As load is increased, more and more of these stages start to operate under pressure. And finally, at full load, only the last few stages of the turbine may actually be under a vacuum. In the stages that are under a pressure, steam tries to escape by finding a weak point in the turbine. Now, this is usually where the shaft penetrates the turbine casing. The steam that leaks out affects the efficiency of the turbine, and it's a waste of money. Allowing steam to leak from a turbine is similar to leaving your front door open in the wintertime. Leaking steam can also seriously burn personnel working around the turbine. The gland seal and the gland seal exhaust systems increase efficiency and safety by preventing these problems from occurring. Gland seals not only prevent steam from leaking out of the turbine, they also prevent air from leaking into the turbine. In the turbine stages where the steam pressure is less than atmospheric pressure, air will try to leak into the turbine. Now, this also reduces turbine efficiency as the air must be removed in order to maintain the vacuum. Air leaking in also can cause the problem of thermal stress to the turbine. That is, the outside air is much cooler than the inside of the turbine. When the air hits the turbine, drastic temperature differences occur. The resulting thermal stress on turbine parts could cause them to crack. The gland seal and the gland exhaust systems prevent this from happening by keeping leakage to a minimum. A gland seal is made up of several labyrinth seals. A labyrinth is defined as a maze or tortuous path from which escape is difficult. Now, as this diagram indicates, the maze in a labyrinth seal is a set of grooves and ridges which correspond to another set of grooves and ridges on the turbine shaft. When properly installed, the labyrinth seal creates a tortuous path that makes it difficult for air to leak in or steam to leak out. Generally speaking, 3 or more seals are used at each sealing point, and these are collectively called a gland. Here you see an example of this. This is the inside of the turbine, and here is the outside. The gland sealing system is connected to the gland at the opening between the first and second seal. The gland seal exhaust system is connected at the opening between the second and third seal. Now, here we can see 2 turbine sections, one high pressure and one low pressure, each connected to the same shaft. Here is the gland seal system, and here is the gland exhaust system. Let's look at the gland seal systems first. A steam supply line, a steam supply control valve, a steam leak-off line, and a steam leak-off control valve make up this system. When the turbine is operating at low loads and is under a vacuum, outside air tries to leak in. In this case, the gland seal steam control valve opens and low-pressure steam is supplied to the gland. Now let's return to our typical gland seal. We can see that part of the steam flows towards the outside past the second seal. The remainder of the steam flows into the turbine. It's the flow of steam towards the outside of the gland that prevents outside air from leaking into the turbine. Steam flowing into the turbine from the glands presents no real problem since, well, it's essentially the same temperature as the steam inside the turbine. No thermal shock occurs to turbine parts, and the leaking steam simply mixes with steam already in the turbine. Okay, we now know that in order for the seal to operate, steam must be supplied to the gland. When a vacuum exists inside the turbine, the gland seal system supplies the steam to prevent air from leaking in. When the turbine is operating at full load with a positive pressure in most stages, the air leaking is not a major problem. Instead, steam must be prevented from leaking out. In this case, pressure in the gland is increased by the steam leaking from the turbine. The steam supply valve closes and the steam leak-off valve opens to prevent pressure getting too high. Steam passing through the leak-off valve is directed to a low-pressure area, such as the main condenser. Now, let's turn our attention to the gland seal exhaust system. By now, you should realize that the purpose of the gland seal exhaust system is to draw off steam, leaking past the second seal before it escapes to atmosphere. A typical gland seal exhaust system consists of the following: a gland steam condenser, one or more vacuum pumps called gland steam exhausters, and connecting pipe. The exhausters draw a vacuum on the entire system, pulling air and steam from the glands into the condenser. In the condenser, steam is condensed, and the condensate is usually drained to the hot well. Air and any other non-condensable gases are discharged to atmosphere by the exhausters. Now, normally, the gland seal and the gland exhaust system work automatically. However, since both your safety and the efficient operation of your unit depends on them, periodic checks are needed. Some of the areas that should be checked include the gland seal steam supply pressure, making sure that it's high enough to maintain the seals without being so high that steam leaks from the glands. The temperature of the cooling water flowing through the gland steam condenser must also be checked. The temperature must be low enough to ensure that condensation is occurring properly. And you also want to make certain that the exhausters are working properly and that there's a vacuum within the condenser. And finally, check that the condensate water level in the gland steam condenser is being maintained at the proper level. There's usually a sight glass that allows you to determine the water level. Now, although the steam seal system we've just seen is probably the most common method of turbine sealing, you should be aware that other methods exist. The two most common alternatives are the carbon seal and the water seal system. Carbon seals are usually found on low-pressure turbines. A carbon seal system consists of one or more carbon rings held in place against the shaft by springs. As the shaft turns, it rubs against the carbon rings, and effective seal between the shaft and the casing is achieved. Carbon, being softer than metal, creates minimal wear on the turbine shaft. Now, eventually, the carbon wears down, so the carbon rings must periodically be replaced. The second alternative to steam seals is water seals. Water is pumped through a special gland to minimize leakage. Water seal systems represent an advantage over carbon seals in that the parts last a long time. A typical water seal has an impeller device mounted on the turbine shaft, which circulates water through the gland. The circulating water fills the opening between the shaft and the casing, and leakage is prevented. Valves in the water supply and return lines maintain proper water temperature and pressure in the gland. Some water does leak into the turbine, and for this reason, shrouding is generally placed around the turbine shaft. Water is collected in the shrouding and drained off by a connecting pipe. We've now seen three methods for sealing turbines. Now, even though these systems are reliable, they still must be checked regularly. Part of the operator's job is catching small problems before they become big ones.